We are searching for a combinatorial object. Such as a subset, a permutation, and so on. In order to search for a combinatorial object, we generate all possible combinatorial objects and then search for an object which satisfies the given criteria. And we call that enumerative search. Enumerative search is what comes close to brute force. Brute force is not a strategy. But enumerative search can be said to be a strategy. One way to implement enumerative search is using backtracking. I will call backtracking a technique and not a strategy. For example, recursion is a technique. Iteration is a technique. Backtracking is a technique. Whereas decrease and conquer is a strategy. Divide and conquer is a strategy. Enumerative search is a strategy. A strategy is at a higher level than a technique. Okay. The solution that we are searching for is a combinatorial object or combinatorial structure. Examples for combinatorial objects are subset, permutation, combination, partition, path in a graph, spanning tree of a graph. These are examples for combinatorial structures or combinatorial objects. Our solution is a combinatorial object. We are searching for a combinatorial object that satisfies a criterion or optimizes an objective function. If we are searching for a combinatorial object that satisfies a criterion, it is a search problem. If we are searching for an object that optimizes an objective function, that minimizes certain value or maximizes certain value, that is an optimization problem. So in this case, in the search problem or in the optimization problem, the solution is a combinatorial structure. We can construct the combinatorial structure by a sequence of decisions. The solution is in the form of a n component sequence. D is a solution. D is a sequence consisting of n components, D1, D2, D3, and so on, Dn, where every dA comes from a set Si. So this solution sequence should satisfy the criterion function in the case of a search problem, or optimize the objective function in the case of an optimization problem. I will give an example. What do you mean by the combinatorial structure as a sequence of decisions? Suppose the combinatorial object is a subset. How can we view a subset as a sequence of decisions? There are n items, 1, 2, 3, and so on, n in a set. We can represent any subset by a n-bit sequence, D1 to n. As we saw yesterday, Yesterday we saw that this kind of representation of a set is known as bit vector. It's a n-bit vector. If item 1 is in the subset, it is 1. If it is not in the subset, it is 0. If item 2 is in the subset, it is 1, otherwise it is 0, and so on. In general, if item k is in the subset, d at k is set to 1. If item k is not in the subset, d at k is cleared. It is reset to 0. So this is an example for how a combinatorial object such as a subset can be represented as a sequence of decisions. Permutation is another example for combinatorial structure. We can view a permutation as a sequence of decisions. There are n items, 1, 2, 3, and so on, n. A permutation is only a rearrangement of the n items. Any arrangement, permutation of n items can be represented as a sequence of n items. Suppose there are 4 items, 1, 2, 3, 4. One can be one of the 4 values, 1, 2, 3, 4. 2 can be one of the remaining 3 values. 3 can be one of the remaining 2 values, and so on. Similarly, a combination is also a combinatorial structure. A combination can also be represented as a sequence of decisions. There are n items, 1, 2, 3, and so on, n. Any combination of r items from an n set can be represented as a sequence of r items, only that here it should be ordered. For example, a sequence can be 3, 2, 1, 4. But a combination is always 1, 2, 3, 4. Whether it is 3, 2, 1, 4 or 3, 2, 4, 1, all amount to the same combination. In a combination, order does not matter. Therefore, we choose a single order. Question. How will you represent a partition as a sequence of decisions? Suppose there are n items, 1, 2, 3, 4, and n, and there are m partition. Then every element in the set belongs to one of the m partition. For example, 1 belongs to either partition 1 or 2 or 3 or m. Let's say this belongs to partition 4. 2 belongs to partition 1. 3 belongs to partition 5, and so on and so forth. Any partition can be represented as a sequence of n integers where each integer is in the set 1 to m. So we have shown several combinatorial structures such as subsets, permutations, combinations, and partitions can be represented by a sequence of decisions. Now we want to construct the sequence. We said we have 2 problems. One is a search problem. The other is optimize. Find the optimal combinatorial object. Find the optimal subset, optimal permutation, optimal combination, optimal partition, optimal path in a graph, and so on. Or search for a subset, search for a permutation, search for a combination, search for a partition, and so on. I will give you 2 examples for the search. For example, suppose you have a 4 by 4 board. And you have to place 4 queens in the board in such a way that all the queens are safe. you cannot place another queen in the same row or same column or same diagonal. Therefore, maybe you may place a queen here and so on. In the third, if you place two queens in this way, you cannot place the third queen here or here. If you place it here, it will be attacked by this queen. If you place it here, it will be attacked by this queen. If you place it here, it will be attacked by this queen. If you place it here, it will be attacked by this queen. So it is not safe. So you may start with something else. So how can I view it as a combinatorial structure? I can view this as row 1, row 2, row 3, row 4. This is row. Row 1, 2, 3, 4. This is column. 1, 2, 3, 4. So in row 1, where should the queen be placed? You can place column 1 or column 2 or column 3 or column 4. In row 2, where will you place the queen? 1 or 2 or 3 or 4. But since we have already placed a queen in row 1, okay, let me say, okay, in row 3 again, 1 or 2 or 3 or 4, 1 or 2 or 3 or 4. Suppose I have placed a queen in, for row 1, I have placed a queen in column 1. In row 2, I will not consider column 1 at all. Therefore, I can strike it out. I will consider only 2, 3, 4. Suppose I have placed in 3. Then here 1 and 3 I will not consider at all. Okay. Therefore, effectively what we get is something like this. You have to consider all permutations of 1, 2, 3, 4. Find a permutation of 1, 2, 3, 4 such that it is safe. So we have formulated what we call 4 queen problem into searching for a combinatorial object, a permutation. Yet another example, magic square. You are given a 3 by 3 grid. You have to, let me number them 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to fill in the 9 squares, 9 cells with one of the 9 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9 in such a way that the sum of any row or the sum of any column or sum of any diagonal are all equal. I call that magic square. If I get rid of this square structure and view it as simply a 9 element sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, the problem asks for a permutation of 1, 2, 3, 4, 5, 6, 7, 8, 9 in such a way that sum of items 1, 2, 3 is equal to sum of items 4, 5, 6 is equal to sum of items 7, 8, 9 is equal to sum of items 1, 4, 7 is equal to sum of items 2, 5, 8 is equal to sum of 3, 6, 9 is equal to sum of items 1, 5, 9 is equal to sum of 3, 5, 7. I am asking for a permutation which satisfies this property, this criterion. Therefore, magic square can also be formulated as a permutation problem. You must think about that. Maybe tomorrow we will try this problem in the lab. So 4 queen.
Sir?
Yeah.
Can Sudoku be considered as a similar problem, sir?
Yes, correct. Sudoku is a much more difficult problem, but it can be viewed or formulated as a searching for a permutation problem also.
Yes, yes.
So I'm starting with very simple problems. 4-queen problem, magic square. As I told you at the outset of the course, don't just take these problems only for algorithm scores. Consider this is a kind of preparation for an interview. Definitely you won't, the time spent on solving these problems is not a wasted time. Just leave alone how you do in algorithm scores, but count it as a preparation for good interviews when you are in the final year. Okay. So what we want to do is, what is brute force? I will say, generate all possible permutations of 1, 2, 3, 4, 5, 6, 7, 8, 9. It will return permutation 1. In all, I will have 9 factorial permutations. I will check, does permutation 1 satisfy the criterion? Does permutation 2 satisfy the criterion? Does permutation 3 satisfy the criterion? And so on. Finally, does permutation 9 factorial satisfy the criterion? And we call that enumerative search or brute force. Okay. How many permutations are generated in 4 queens problem? For magic square, we enumerate 9 factorial permutation, search for one permutation which satisfies the criterion. How many permutations are generated for 4 queens problem?
24, sir.
Pardon me?
24, sir.
You mean 4 factorial?
Yes, sir.
Yeah, 4 factorial. So in one sense, this 4 queen problem is easier than magic square because it has to examine 9 factorial permutations, whereas 4 queen problem has to examine only four factorial permutations. We may also have 8 queens problem. In general, we can have n queens problem. Okay, how are we going to solve it? Backtracking is a very simple but very powerful method. Algorithm, I name it solve. My permutation is an array D. You may call that this is an array. Array D is an array or list or sequence or tuple in whatever way. I will call this array. So the complete solution is D1 to N. In the case of 4 queens problem, the complete solution is D1 to 4. D1, D2, D3, D4. In magic square, it is D1 to 9. D1, D2, D3 and so on, D9. All the 9 values have to be initialized such that the given criterion is satisfied. How we will do is, first we will put a value in D1. We will put every possible value in D1. What are the possible values? You can put 1 to 9, anything. After that, the remaining problem is, okay, I will call this a partial solution. The remaining is 2, 3, 4, 5, 6, 7, 8, 9. In 2, put every possible item. That would mean whatever we have put in 1 should be removed. Suppose we have put 3 here. Here you can try 1, 2, 4 and so on. Suppose we put here 6. 1, 2 is a partial solution. The remaining input is 3, 4, 5, 6, 7, 8, 9. In 3, put every possible item. So you have 1, 2, 4, 5, 7 and so on. This is the basic idea. In how many different ways the given problem can be decomposed into subproblems? Suppose Okay, we start with a problem of size 9. All right. Now, we want to solve the problem. How many different sub-problems can we obtain? Can you try to answer this question? We start with a problem of size 9. In how
Size
many?
8.
Root
Yeah,
power 9.
no.
Uh,
Size 8, I agree.
Eight.
Okay. The given problem size is 9. The sub-problem size is 8. That is agreed. I am asking you, how many sub-problems do we arrive at? Or do we decompose it into?
So I don't understand. So like if let's say we fill a value at 1, at
Hmm.
person 1, then we need to consider a sub problem of size 8.
Okay. Yeah, I understand your difficulty. Can I put a value such as 5 here? Okay. And I have decomposed the problem into a sub-problem of size 8. If I solve the sub-problem of size 8 and item 1 is 5, can I solve the problem?
Maybe or may not be so.
Maybe or may not be. Cannot at all. I need to solve a sub-problem of size 8 with item 1 is equal to 5. I need to solve a sub-problem of size 8 with item is equal to 1. I need to solve a sub-problem of size 8 with item is equal to 2. I need to solve a sub-problem of size 8 with item is equal to 3. So how many sub-problems do I need to solve?
Oh, okay.
9.
9 factorial.
Not 9.
9.
9
Oh,
is the
okay.
answer. Item 1 can be 1. With item 1 is equal to 1, solve the sub-problem. With item 1 is equal to 2, solve the sub-problem. With item 1 is equal to 3, solve the sub-problem, and so on. With item 1 is equal to 9, solve the sub-problem. So in all, I have 9 sub-problems.
Oh, okay. I started considering with for
Yeah,
a sub problem after 1 is filled, then how many sub problems?
right. Okay. So once we have solved 9 sub-problems, we can construct, let's say, 9 solutions. I mean, not 9 solutions, 9 candidate solutions. Out of the 9 candidate solution, whichever satisfies the given constraint. What is the given constraint? All rows, all columns, all diagonals sum to the same value. So we have 9 sub-problems and 9 candidate solutions. Which of the 9 candidate solutions satisfies the magic square condition, the magic square criterion? That is the solution. Okay, contrast this with the situation that we have been dealing with up till now. In decrease and conquer, we always decompose one given problem to one sub-instance, one sub-problem. In divide and conquer, one sub-problem may be decomposed into 2 sub-problems, or maybe 3 sub-problems, or maybe 4 sub-problems, not more than that. Whereas here, we are decomposing, I'm sorry for this noise. One sub-problem has been decomposed to 9 sub-problems. In the case of 4 queens problem, one sub-problem will be decomposed into 3 sub-problems. Suppose it is n queen problem, it will be decomposed into n minus 1 sub-problems. Contrast the situation. At one extreme, we have decrease and conquer with just one sub-problem. At the other extreme, we have n minus 1 sub-problems. Okay. And therefore, this is exhaustive search or enumerative search. Input is a partial sequence D1 to K. Maybe I have already put values in 1, 2, 3, 4, 5. The remaining input, let's not worry about that. Okay, we have put some values, maybe 2, maybe 6, maybe 1, maybe 4, and so on. Consider all possible ways in which we can complete the solution. What are the possible ways in which we can put values to 6, 7, 8, 9? So complete sequences D1 to N, which is a super sequence of D1 to K. I have abused the superset notation. This means D1 to N is an extension. D1 to K, K plus, okay. This contain the entire D1 1 to K. In addition, K plus 1, K plus 2, K plus 3 and so on up to N are put values. So complete sequences satisfying search criterion have been printed. We are going to formulate this as a recursive algorithm. Any recursive algorithm should have a base case, at least one base case, and a recursion step. The base case is if K is equal to 1, the precondition is items 1 to K have been initialized. If K is equal to N, that means items 1 to N have been initialized. We have put values in all the items, in all the slots 1 to N. Then all that we have to do is check whether D1 to N satisfy the criterion. What is the criterion? In the case of 4 queens problem, all the 4 queens are safe. No queen is under attack from any other queen. That means no 2 queens are in the same row, and no 2 queens are in the same column, and no 2 queens are in the same diagonal. That is the criterion. In the case of magic square, the criterion is, we have already said, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 4, 7, 2, 5, 8, 3, 6, 9, 1, 5, 9, 3, 5, 7. All the rows, all the columns, all the diagonals sum to the same value. That is the criterion. Example. If the criterion is satisfied, then it is a solution. I use the two words candidate solution and solution. A candidate solution is likely a solution. If all the n items have been put values, it is possibly a solution. If it satisfies the criterion, it is a solution. So distinguish between the two words, candidate solution and solution. Okay. Now about the recursion step. Items 1 to k have been initialized, and we want to put a value for item k plus 1. For k plus 1, what are the choices? How do I find out the possible choices for k plus 1? Given items k1 to k have been initialized and I is the remaining input, from these two parameters, I can find out the possible choices for k plus 1. For each choice in choices that I have calculated, put that value in dk plus 1. The input was 1 to k have been given values. Now we have extended that to k plus 1. All right. For example, 1, 2, 3, 4, 5 have been given values. Now we put a value here and then we say complete the rest of the sequence. Solve D1 to k plus 1 and reduce to I. For the time being, do not worry about this reduce to I, this I, this I. Look at that. Is it a recursive algorithm or an iterative algorithm? Just because there is a loop for each choice in the possible choices for k plus 1 does not mean it is an iterative algorithm. Only that if it was a decrease and conquer, there was one recursive call. If it is a divide and conquer with two subproblems, there were two recursive calls. If it is a divide and conquer with three subproblems, three recursive calls. Four subproblems, four recursive calls. In the case of exhaustive search with backtracking, we really do not know how many subproblems will result. If the problem size is 9, there may be 9 subproblems. If the problem size is 8, there may be 8 subproblems, and so on. Therefore, because we do not know the number of subproblems, there is a loop here. It's a very simple algorithm, but very powerful. I mean, we will talk about a lot of things about backtracking, exhaustive search in the coming weeks. But this is one algorithm you must have mastered. How will the algorithm change if it is? Okay, for the time being, I do not discuss this algorithm. What the only change I have done is look at the place where I check for the criterion. When I have a complete solution, I mean a likely complete solution. When I have a candidate solution, I can check for the criterion. I have put all the values, all the 9 values, and then I can test whether it is a magic square, or I have put all the 4 values and I can check whether it is a safe placement of queens. I can move this criterion checking from here to here. Check here. Do not wait until all the n values have been put. Even when we have put only k values or k plus 1 values, test whether the k plus 1 values that we have hitherto put satisfy the criterion. And the resulting algorithm is this. Homework. What is the advantage of testing for the criterion here versus here? By the way, we are testing for the criterion in a candidate solution in this place, in the farmers. This is we are testing for the criterion with a partial solution.
Sir, I think I may have an answer.
Can you tell the answer?
Yes, sir. So a candidate solution is a complete solution, as in the algorithm needs to have run to completion for one iteration. Then it becomes a candidate solution with all the let's say array elements populated.
Okay.
But for a partial solution, we can check directly with a half populated array. So let's say if in a queen problem, the first element is 1, and we fill the second element with 1 as well. In that case, it will be rejected immediately if we check the criterion inside the for loop. But when we go for the candidate solution, the 1 and then some need to be filled for it to be a candidate solution, and then it will be rejected. So we are reducing a lot of unwanted population in that case.
What's the name?
Pradeep, sir.
Great. I mean, wonderful explanation. You are right. This idea is called pruning. More on it later. Okay. How does backtracking work for optimize? I have only copied pasted the search with backtracking and made some changes. Look here, this does not change. It is the same. Here is the only change. If you want to convince yourself, look at the algorithm. I have this is search with backtracking. This algorithm I have copied, pasted here, and there is a global variable best cost and best solution outside this algorithm. These two. Global variables. Whenever I have a candidate solution which passes the criterion, I will calculate the cost of the solution. Even though I use k, actually since k is equal to n, this is n, this is n, this is n, this is n. If the cost of the candidate solution is better than the current best cost, oh, I have found a better solution. Therefore, I update best cost with cost of the candidate solution, and the best solution itself is updated to be the current candidate solution. Okay. When the algorithm runs to completion, the two global variables best cost and best solution will contain the best combinatorial object and the cost of the combinatorial object. The argument that I made for moving criterion from here to here still holds good. and therefore we have another version of the algorithm. Okay, let's go on. Brute force. Generate all possible combinations of D is equal to D1, D2, and so on, Dn. They are candidate solutions. How many combinations are possible? Suppose D1 comes from S1, D2 comes from S2, D2 comes from S3. S3 is the set of all, S1 is the set of choices for D1, S2 is the set of choices for D2, S3 is, sorry, Sn is the set of choices for Sn. If the sizes are M1, M2, and so on, Mn, then M1 times M2 times and so on, Mn combinations are possible. The combinations which satisfy the criterion or optimizes the objective function are the solutions. If we simplify and assume that all dA are from the same set S, which is of size m, then there are m power n combinations, m times m, this is n times, this is equal to m power n, exponential time. Therefore, brute force never works almost. Some technical words. The algorithm traces a tree. When the algorithm is executed, its history will be a recursion tree. If 4 values are possible for each DI in D1, D2, D3, D4, then the recursion tree has 4 power 4, which is equal to 256 nodes. The nodes of the tree are generated or traced in pre-order. Typo. For example, this is 4 queens problem. Okay, we start with a empty array. Then item 1 may be 1, or item 1 may be 2, or item 1 may be 3, or item 1 may be 4. This means the queen is for row 1, queen is in column 1 or placed in column 2 or placed in column 3 or placed in column 4. Then for row 2, if we follow this branch, already column 1 has been taken. Therefore, in row 2, the queen may be placed in column 2 or 3 or 4. This actually means 1, 2, 1, 3, 1, 4. Okay, then row 3. Already 1, 2 has been used here, and therefore this will be 1, 2, 3, 1, 2, 4. This will be 1, 3, 2, 1, 3, 4. This will be 1, 4, 3, 1, 4, 2, and so on. And finally, this is row 4. 1, 2, 3 has been used. Therefore, 1, 2, 3, 4. This is a candidate solution. At this point, we will check whether this candidate solution passes the criterion test. Or queens in columns 1, 2, 3, 4 in rows 1, 2, 3, 4. Is it safe? It is not safe. How about this? This is 1, 2, 4, 3. Apply criterion. This is safe? No, not safe. This should be 1, 3, 2, 4. Sorry. 1, 3, 2, 4. Is this safe? Not safe, and so on. Okay. So when the algorithm runs, this tree is traced or generated. In which order? I have shown the order here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. 65 here. The numbers inside the nodes, inside the circles, show the order in which the nodes of the tree are generated. This order, by the way, you know to be pre-order. Each node is a state of the process. Each edge is a possible choice for the next value. Nodes in this recursion tree are called states. Choosing a value for dk plus 1 in a node corresponds to an edge from that node to a successor node. The entire tree is called state space. Each node has a partial sequence. For example, if you consider this node, this is okay. This is 2, maybe this is 1, 3, 4. This would be 2, 4, something like that. So each node has a partial sequence D1, D2, Dk corresponding to the path from the root to the node. Nodes having all the components of a n sequence are called candidate solutions. They are likely to be solutions. They will be solutions only if they pass the criterion test. State nodes may not have all the n components. States are nodes. Only the leaf nodes have n components. A candidate solution is a path from the root to a leaf. Since the tree has all possible paths from the root to the leaves, it has all possible candidate solutions. We are searching this tree for a solution. This tree of all possible solutions is called solution space. I skipped this slide and come to one last problem. Okay, we want to generate all permutations of n items, 1 to n. This problem could also be changed to all permutations of r items taken from a n set. That is 1, 2, and so on n. You have to take a subset of r items, not subset, permutations of r items. But to start with a simple problem, there are n items. We want to consider all possible permutations. It constructs each permutation in the array A1 to n as a sequence of n decisions. That would mean one, 2, 3, 4, and so on n. We will first put a value, put the possible choices in item 1. Then possible choices in item 2 and so on. That is what we mean by as a sequence of indecisions. Let's say each recursive call receives a partial sequence. This is m plus 1. So m plus 1 to n, we have already put values. And the call itself will put an additional value. This is already done. We have already put values in m plus 1 to n. And we will put a new value in m. We are extending it. Of course, I could have started from 1 also. 1 to m, we have already put values and we want to extend it to m plus 1. That is how I presented the backtracking algorithm. So you can change it. So a m plus 1 to n is the input. We extend it by one item, one component to a m to n. That means in a at m, you have to put every possible choice. But in a permutation, for a at m, we have to use only those items which are not used in m plus 1 to n. Am I right? If you have already used, say, 2 and 3, 2 and 3, we cannot try 2 and 3 here. Therefore, we need to keep track of the items used in a at m plus 1 to n in a Boolean array used. We will maintain a Boolean array used. We initialize all the entries in the Boolean array to be false. To start with, none of the items 1, 2, 3, etc. n are used. If used at j is equal to true, then item j has already been used in the subarray a m plus 1 to n. Therefore, the algorithm is here. This is a backtracking algorithm. How do we use backtracking to generate for enumerative search? This is the last slide. Permute m. Input is a partial solution, a m plus 1 to n. This is m plus 1. This is n. This is already, we have put values. And we want to put a value here. output all A1 to N, that is complete solutions, which are extensions of A at M plus 1 to N have been printed. This is the base case. This is the recursion step. What is the base case? If M is equal to 0, what does that mean? 0 plus 1 is equal to 1. So 1 to N is the input. That means this is 1. All the elements have been initialized. Therefore, this is the candidate solution. For generating permutations, we don't have a criterion. If all the items are given values, it is a permutation. Therefore, simply print A at 1 to N and return. Okay. It is not a complete solution. What should we do? We have to put every possible choice in M. For J is equal to 1 to N, we want to put a value in A at M. Every possible value for A at M is J is equal to 1. J is okay. A at M, we can put the value 1 or put the value 2 or put the value 3, put the value N and so on. But there is a condition. We can put only those values. This is the choice. We can put only those values which are not already used. Okay. Therefore, here is a condition, conditional clause. If J is not used in M plus 1 to N, basically what we are doing is from 1 to N, we put a filter and we get only unused 1 to N. Not all values of 1 to N. If J is not used in N, then we can use it for use it as a choice for A at M. Okay. And we want to make sure subsequently when 1 to M minus 1 are initialized, the J that is used to initialize A at M should not be used. Therefore, used at J is set to true. And then we are calling it, we are making a recursive call, permute M minus 1. That means M to N have been initialized. We are looking forward to putting a value in M minus 1. Very important. After this call, permute M minus 1 returns, we are no longer using the value J. Therefore, it can be released with used at J becomes false. You must think carefully about this code. Homework. How will you modify this algorithm to generate combinations? Remember, this is backtracking. I have copied, pasted the first page backtracking algorithm and made a few changes. That's all. So basically, it's a backtracking algorithm. So 1, 2. Modify the algorithm to generate N choose R, all possible combinations of R items, N items taken R at a time. That's all for the day. Maybe for tomorrow's class, implement this algorithm and also magic square and also 4 queen. I mean, don't think that this is such a great, so many problems. All we need to do is one backtracking, that's all. That one backtracking gives us permutations. That one backtracking gives us combinations. If you want subset, I'm not using that. And you can use permutations. Either you can use the generation of permutations as a sub-algorithm, a function call to solve magic square and 4 queen, or you can make use of the same outline of the algorithm to solve magic square and 4 queen. There is no need to worry about pruning for the time being. You need to, it's okay if you apply the test only for candidate solutions and not on partial solutions.